Good morning, everybody. My name is Dr. L. Lakshmi, Assistant Professor, Electronics and Communication Engineering Department, G. Polarity Engineering College. Welcome to the lecture series of Electronic Circuit Analysis. In the previous lecture, I explained about the importance of H parameters and how we have to calculate the H parameters and why we have to calculate the H parameters. And finally, I framed the internal structure of a transistor by using hybrid model or H parameter model. Today's discussion, we concentrate that why we have to name it as H parameter. And how we have to convert a practical circuit into AC equivalent model or H parameter model. Conversion of practical circuit into AC equivalent model. These are the two important things what we have to consider in today's lecture. So first of all, what is the need of why we have to use the word as H parameter? The name itself, we can understand that H is nothing but hybrid parameters. Why we are calling as hybrid parameters? As we know that we are using 4 parameters in order to understand the internal model of a transistor. And these 4 parameters explains the behavior of resistance, dependent voltage source, dependent current source, and as well as output resistance. Once again, I am trying to highlight the importance of H parameters. One is HIE, whereas which explains the behavior of resistor or resistance. HFE, which explains the dependent current source. HRE, dependent voltage source. HOE, output admittance. Now you try to observe that the first parameter is explaining the resistive behavior, and the second one is current behavior, and the third one is voltage behavior, and the HOE will explain the admittance. That's why it is not stick on to a single parameter. It consisting of a combination of 4 different parameters. That's why it is called the hybrid parameter. Hybrid is not belongs to the single type. For example, before coming to the H parameters in electrical circuits in two-port network, already we know that Z parameters, Y parameters, ABCD parameters. So here in Z parameters, all parameter explains the behavior of impedance. Whereas in Y parameters, all will explains the behavior of admittance. And ABCD parameters explains the behavior of current as well as voltage, I and V. So particularly belongs to a single type, whereas the H parameters is a combination of different parameters. That's why it's called the hybrid parameter. Now, how we have to convert this hybrid parameter into a, of course, how we have to convert this practical circuit into a hybrid parameter model. So before going to the conversion, I am trying to highlight the once again the important equations what we are coming across. So depending upon the dependent parameters, we are trying to frame this equation. As we know that from the forward bias and the reverse bias of input and output characteristics of a transistor, we are trying to highlight that VBE is a dependent parameter and IC is also a dependent parameter. And if you consider the equation can be explained that HIE IB plus HRE, VCE. Similarly, in the second equation, we can frame it as HFV, IB plus HOE, VC. These are the two equations what we are using for H parameter model. The first equations will obey the principle of Thevenin's equivalent, and the second equation will obey the principle of Norton's equivalent. According to that, I am trying to frame the internal structure of a transistor by using a dependent voltage source and dependent current source consisting of input side with a resistor and the output side a parallel resistance which is parallel to the dependent current source. Now you consider the common emitter configuration. In this common emitter configuration, we are considering the emitter is common. These emitter what we are considering by drawing a practical circuit where the emitter resistor consisting of parallelly bypass capacitor, this is RE, and the biasing resistors, and consisting of a load resistance RC, this is DC, IC, of course, this RL, and the input coupled capacitors C1, C2, R1, R2, biasing resistors, and consisting of a AC source, which are everything is grounded, the emitter of NPN transistor. Now I have to convert this circuit into AC equivalent model. So to convert the circuit into AC equivalent model or hybrid model for a given practical circuit, we have to follow two conditions. That the first condition is there any DC sources in the practical circuit? We have to make it as 0, so that all DC sources are grounded. All DC sources are grounded. This is the first condition what we have to consider to convert any practical circuit into AC equivalent model or hybrid equivalent model. The next condition is all capacitors in that circuit are short circuit. All capacitors are short circuit. Why? Because for AC, the capacitors is allowed. For AC signals only, the capacitor will allow. For DC signal, capacitor will block. That's why we are making the AC analysis. First, we have to convert the given practical circuit into AC equivalent model. And for that purpose, we require the AC analysis. These conditions we are considering as AC analysis. So, the first condition is make all DC sources are grounded and all capacitors are short circuit. Okay. Now we used to apply these conditions in the above practical circuit of common emitter configuration. So this is the common emitter configuration we are using for an amplifier. So finally, the amplifier consisting of common emitter configuration. Of course, it is an amplifier. Why? Because the AC signal is applied and the DC supply is applied. In order to move the transistor into the active region, then only we are applying the AC signal. And these R1 and R2 are the biasing resistors, and RE is the emitter resistor or feedback resistor, and C is a bypass capacitor. If you want to use or if you want to apply any signal to this particular circuit, first we have to see that whether the transistor is operated in active region or not. For that purpose only, first initially I am applying the input side as forward bias, where NPN, P is base is a P type of terminal, where the base is connected to the positive of the AC source, and here the biasing condition what I am applying, that the input is VCC, where the positive terminal of the DC supply is connected to the positive terminal of the base. That's why input side is in forward bias. Where the output we are taking across the collector, and the collector which is having the connection between the output side, between the collector and the emitter. Collector is a N type of terminal, which is N is connected to the positive terminal of the DC. The output is reverse bias. By observing inside the practical circuit, we are concluding that the transistor is operated in active region, and that too the emitter is grounded. Input I am applying across the base terminal, and the output is taken across the collector terminal. That's why it is called as common emitter configuration. So I am checking the three conditions in the practical circuits. One is whether the DC supply and the AC signal is applied or not. And the second thing is input is forward bias and the output is reverse bias. The third thing is what type of configuration, that at input at which terminal we are applying and the output from which terminal we are taking. These are the three things what we observed from the practical circuit. Now I have to apply all these two conditions on this practical circuit, and finally I have to simplify the circuit, and after that I have to convert the internal structure of this transistor into hybrid equivalent model. So now you see here, what is the first condition? DC, making DC sources as 0. And the second condition, all capacitors are short circuit. So by considering these two conditions, I am making that, for example, I am making short circuited. The input coupled capacitor is short circuited and biasing resistors. And this is the emitter resistor, which is shorted by the capacitor. Why? Because all capacitors are short circuited, and the output I am taking across RC. Here I am making VCC as 0. In the previous slide, I am considering VCC as some value, but I am making VCC is equal to 0. Nothing but I am making VCC as grounded, like this, RC. And here also this is grounded, because VCC is 0. And the output is short circuited because of coupled capacitor. Here C1, here C2, these two are short circuited. And in the output side, which is grounded, that is RL. And this is the input signal, what I am applying. This is grounded. This is R1, R2, and this is R. This is a circuit by applying the two conditions what I am coming across in the previous one. These are the two conditions I am applying. After applying these two conditions on the above circuit, the resultant circuit will be like this. Okay. Now we will see, we will have a little bit more simplification here. Once R1 is grounded, we can move this R1 parallel to R2 by observing like this. So I am trying to move this R1 parallel with R2, and this is the resistor. Now if you carefully observe that in the previous circuit where the capacitor is short circuited, as capacitor is short circuited, the effect of RE is nullifying. So the effect of RE is equal to 0. That's why I am making as there is no effect from RE. So obviously I am considering as short circuit. And in the output side, RC is there. I used to connect this RC, which is grounded. This ground I can connect parallel to RL, so that I can make RC parallel with RL, which is, this is a simplified circuit what I am making by making DC sources as 0, all capacitors are short circuit. We will try to apply now the AC equivalent model to the internal structure of the transistor, and once again we will try to draw the final amplified circuit like this. So input is short, where R1 is parallel with R2. This is AC source, and the input transistor is equivalent to a hybrid model consisting of resistance as HIE and the dependent voltage source HRE, DCE. This is IB, the dependent current source HFE, IB, and HOE. And finally the output resistance as R0, which is parallel with RC. And here also R1 parallel with R2 I am considering as RP. If you carefully observe here, this is the output current IL, is going across R0, and this is the IC current, what we are achieving. The base is input and the output is collector, whereas emitter is common, which is grounded. The emitter is common between input and output side. And this part will explains us the hybrid model of transistor. This part will explain the hybrid model of a transistor, where I am trying to frame this model by using 4 parameters: HIE, HRE, HFE, and HO. Simplified circuit, once again I am trying to draw here the simplified circuit from the above circuit, where I am considering as RP, HIE, HRE, VCE, and AC signal is applied. This is at input side, and the output side is a dependent current source, HFE, IB, source HOE, and finally R0. So this is IL, this is IC, this is IB, this is filter is common. Input I am applying across the base. This is the final circuit what we are achieving from the practical circuit what you are getting. This is one of the practical circuit, and this circuit is converted like this, unless until if you are not able to convert this circuit into hybrid equivalent model, not possible for us to find out the voltage gain, of course current gain, voltage gain, input resistance, and output resistance. In order to find out these 4 parameters, we have to convert the circuit into hybrid equivalent model. That is the first step. Once you convert any practical circuit into hybrid equivalent model, then after that, from that model, we will try to extract all the parameters of that. Similarly, we will go for one more circuit to convert a practical circuit into hybrid equivalent model. For example, I am considering common collector amplifier, which having the common collector configuration. Common collector amplifier is first initially obeying the common collector configuration, where input is base and the output is emitter. So it is also called as emitter follower circuit. We'll consider the practical circuit, and from that we'll try to convert into AC equivalent model, and after that we'll try to extract the parameters of the amplifier. So here the biasing resistors R1 and R2, the output is taken across RE, and which is grounded. Just now what I am coming across, the configuration what we used to prefer is a common collector, and this is VS. VS or V input. So input what we are applying, that is V input, and here we are applying the VCC. And I am taking the output was here, C1 and C2, emitter, base, collector, which is a NPN transistor. I am applying the input across the base terminal, and output is taken across the emitter terminal, where collector is a common. That's why it is called the common collector. And it is calling as emitter follower because whatever the variations we are observing across the base terminal, we can observe the same variation across R. Why? Because both are in same phase. The phase shift between input and output of common collector amplifier is 0 degrees. Whereas in the previous case, the phase shift between input and output signal is in 180 degrees. Because in common emitter configuration, we are applying the input across the base terminal and output is taken across the collector terminal, whereas the base and collector terminal both are superimposing, nothing but both are in opposite direction. So that's why we are getting the phase shift is 180. That is also a very important point what we have to consider. Phase shift in common emitter is 180 degrees. Whereas in the second case, phase shift in common collector is 0 degrees. Why? Because the emitter current and base current both are in phase. That is the reason. Now we have to convert this circuit into AC equivalent model. We used to apply the same procedure as we know that